All right, good morning, everyone. I am going to go ahead and stop sharing this introductory slide and turn it right on over for our training speaker this morning. So please go ahead, Henrik.
Hello, thank you very much for the introduction. I'm Henrik. I will give this training on adding a transport equation to scalarTransportFoam. And I'm working for Wiki. We are a consultancy company offering support, training, and contract development for OpenFOAM. So most of the training will be very interactive, and you can use the chat for this. This is the first time that I do this online. So usually I have all the people in the room, and people can shout at me when I do things wrong during the training and can ask questions. And I would like to do that the same way but through the chat. So please type any questions in the chat while I'm doing the training. And I hope we can maintain the interactive manner of this training as much as possible. So I will switch off the video so you got an idea on who is giving the training, and now you can concentrate on my screen. Okay, and I need to add the chat here. Okay, so can you all see the screen?
Yes, we are able to see the screen. We cannot see the chat though on your screen. So if you get a chat directly to you, that's a question.
Then I need to repeat the question.
Yes, I would suggest it.
That is perfect. Okie dokie. I can see the chat. That's the good start. And is the font good enough?
Looks good to me, but people are free to.
I'm just trying to see if there's anybody at the other end.
Yes.
Okay. Sometimes you have to, yeah, just live with the silence. Okie dokie. This is some leftover. Okay, so I have opened the terminal. I have OpenFOAM. I'm using Foam 4.1 for historic and my personal reasons. You can do the same thing with any other version of OpenFOAM in principle. There are some issues with some differences between the versions, as you know. OpenFOAM is a bit lighter. So if you use some other versions, you might find things like FV options and stuff like that, but don't be distracted with that. The training is not really meant for you to follow by typing. I will be probably too fast when I start changing the code. But I really would like you to put questions and ask questions during the training and make recommendations. And you can. It doesn't follow a fixed schedule. I have a plan that is outlined in the title, and the plan is to take scalarTransportFoam and add another transport equation to it. Herv just said we lost audio. Okay, so there seems to be a problem. It seems to be okay to most parts of the world, but not to Great Britain. Okay, I'll continue. So shout if there is a problem with the audio. Okay, so adding a transport equation to scalarTransportFoam. So scalarTransportFoam, in case you don't know, is a very small solver in OpenFOAM. It solves a single transport equation, the standard transport equation. And as you know, it is consists of a time derivative, convective, and diffusive transport. And that's pretty much all it does in its raw version. The grand plan of things is we will take the source code, I will copy it out of the distribution and start modifying it. And we'll take a test case, and we will also go through the code line by line, explaining you bits and pieces of the source code. Okay, so in the hope that you understand the basic elements of OpenFOAM, and then you will be able to add another transport equation. This will be very much intuitive because of the nature of OpenFOAM and its ability to mimic standard transport equations. Okay, so the first thing we need to do is copy the source code for scalarTransportFoam, and I loaded my environment. So I have, if I can demonstrate that by starting scalarTransportFoam. Okay, and as you can see, it comes up with a header. It says I'm in version 4.1 of Foam Extend, and it bails out with an error because the directory I'm in is plain and empty. So there is nothing that scalarTransportFoam would be able to run. But at least you know what I'm running. So if I would like to pick up the source code, how would I do that? Does anybody have an idea? Where would I find the source code? Okay, so I type source, I turn return, and now I have a look where I am. And that took me into the source directory of OpenFOAM. Under applications. So, well, shall I try app? Thanks for helping. Yep. Okay. So these are not standard Unix commands, source and app. They are something that the OpenFOAM environment brings with it. And it is, there are bash or shell aliases. And they don't do anything else than changing the directory to some set variables. So if we look at the aliases, we can find out that source is going to $foam source, and app goes to $foam underscore app. Okay, so so I will have a look here. I'm now in app, as you can see, and if I do look around here, there is a number of directories, solvers, utilities, and this is the basic difference. Utilities are things that you would run for pre-processing or post-processing. Solvers are the things that actually do the work. And but I would like to come back to the source, which was our initial suggestion from the chat. I'll have a look in source, and that has a lot of directories, and those are the libraries that OpenFOAM consists of. So in source are the building blocks that OpenFOAM is made of. Finite volume discretization, it's here, and the main library Foam. And if you have a vanilla version, then it will be called OpenFOAM. Anyway, so that was written in the chat. It was slightly wrong answer, but if we go to app and we have a look here, then there is solvers. That's obviously the place we want to go. And then there is different kinds of solvers. They are sorted by physics segments. So we have incompressible flows, we have heat transfer, and various other things. Our solver resides in BASIC. So, because it's so simple and it doesn't really have a physics segment that it covers, we can find it in BASIC. And here, down there, second line is our scalarTransportFoam. Okay, and here you see the source code, and we'll have a look at it right now. So I'll open this up. I'll use gedit. In this case, any file editor will obviously do. But in this one, I got a question. Okay. Then that has been moved. So the question was, are the folders organized differently in Foam version 5.0? I see many of those folders, but not app in the source directory. Well, app is actually applications, but they may have moved it under source. The nice thing is, because of the aliases and the variables, if you use those, it will always take you to the right location. So unless those are changed. But that is the same over all the different versions. Okay. So I think the main difference that you learned now is that app is an alias, and it changes directory that is fixed by an environment variable called foam app, but the actual folder is called applications. Okay, so we opened the scalarTransportFoam.c, and this is a pretty standard C++ code. The main function starts here. It's called main, and that is the same in all C++ codes. And it is very short. That's why we can go through it in this training. It has only 60, 70 lines of code, and most of it is actually a big header. So, does anybody know what these includes do? These hash includes? Oh, people fall asleep. Okay. Yeah, so it includes some other code. In fact, it includes a file. And the name of the file is this fvcfd.h. And this is something that is done by the compiler in a pre-processing step. So what the compiler does is, in the first step, it goes through this code and finds all these hash includes and inserts the contents of this file in here. And there are various reasons why you would do that. And one is code duplication, but also a lot of C and C++ of the language relies on this mechanism as well. And so this is actually something that is not even C++, but also C. And it's very mechanical. So if I look at fvcfd, for example, okay, the first thing in this directory, it doesn't exist. So this file exists somewhere else. And the way that the compiler knows where to look is on the compile line. So if you do wmake, which is the make system, it outputs a flipping big line. And all of these minus capital I lines, it tells the preprocessor, the compiler, to look in this directory for the files in the include statements. Okay, this can be a bit tricky to find out. So my way of finding out where this file actually came from is by looking into the dependency, which is created by the make system. So if we look in here and we go for fv CFD, then I have a line here, and this tells me exactly where to find FVCFD. So we can open this up. I need to modify it. There is a variable in here. And what you see here is the content of fvcfd.h. And yeah, there is a bunch of more includes in here. Okay, there was a question which has been answered on the chat. So I think I don't have to repeat that one. So that was the question, include with angle brackets and with double quotes. And yes, the one with the angle brackets is for standard headers and system headers. And the other one is for the files that belong to the project or other projects. It also changes the searching and the includes and things like that. Anyway, okay, so these two, they include bits and pieces of OpenFoam headers that put in, enrich, if you want, define classes that are used in the scalarTransportFoam application that you see here. Okay. So now, if we go a bit further, this is where the program starts. So this is the first line, if you want, that is executed. Well, this one is an include, but whatever is in here, it will be the first line that is executed, the first statement in the program. So we can try and find out where that is. Said, oops. Okay. So set root case is a piece of code, and this is the first line that is executed, which parses the command line, the arguments that are coming here from that are put in on the command line. So if you type, for example, scalarTransportFoam minus help, then this will end up in these variables and is passed in this command. Okay, so what is so different between this file and the files that are included here? Does anybody know? Well, maybe we didn't dive deep enough into these files here, but what I can tell you is that if we dive a bit deeper into the levels of include, then, for example, in simple control, if we go there, maybe then it becomes a bit more. Maybe then becomes more clear what I'm trying to ask. Yeah, simple control. Okay, so that one defines a class. So this is the header file, it's included there, and it starts with class simple control. So this defines a class definition. Okay, fine. So these are class definitions, okay, in various levels. And this, what is set root case? Well, this is actually not a definition. This is an executable piece of code. It goes, this defines a variable, and this one is an if statement. Okay, and if you ask a purist, then he will tell you that this is really, really bad. You shouldn't include executable code like this, or at least not call them .h. So that is a bit confusing. I just wanted to mention it because I get asked that, got asked this quite a few times. So, but this also explains it, all of these includes that live inside of the main. They must be, they can't contain definitions because that is not allowed in C++. So these bits here contain code that actually does something. And the most prominent one is actually this one here with the create field. This is where a lot of the global data structures and working arrays are defined. So I'll skip over these because they don't do, well, they do a lot, but I need to skip it somewhere. This is passing the command line. This one is setting up the object registry. I'll come back to that. And here is the mesh is red. I'll skip over the simple controls. And the next stop I want to take is create field. Okay. Create fields. So in create fields, you see a lot of statements that look pretty much the same, like this one. Or this one. There's a lot of similarity in these statements. I'll come back to that. Okay. Can anybody tell me what this does? What does this statement do? A temperature object. Okay. So this is in C++ jargon, this is called an instantiation of an object. So the object is T. Or if you're coming from another language, be it Fortran or C or whatever, this is a variable. So T is a variable. So, and the type of this variable is this. It's a volume scalar field. Or yeah, so T is of type volume scalar field. And if I want to make this simpler, I could think of another statement and call it int a equals 0, for example. That obviously doesn't do the same as this statement, but it's comparable in the sense that it creates a variable, in my example a, and assigns a value to it. Our statement here does a lot more. And essentially, what it does is it creates this variable by reading the temperature from disk. And I'm sure you had some exposure to OpenFoam, and you know the way that we specify fields on disk. So if you go to the 0 folder, there is 0.u or 0.t, and you can change boundary conditions and the field value, and you can change the dimensions. You can do all of that in the file. And the place where this file is actually read into memory is right here. There are a few more things that are happening in this statement. And one thing is the registration of the object with the object registry. It comes here as the mesh, but its underlying is the object registry. And the object registry has a number of purposes. And probably the most important ones is, well, it gives us means to bring the data into other parts of the code. So we can look up these fields from anywhere in the code. For example, in the boundary condition, if you need another field, you can look it up there. This is only possible because the field is registered in the database, in the object registry. So, and this is also happening here. And the other thing is that the object registry keeps track of time. So it keeps track of when should a field be written, for example. There is other things that the object registry does, but I think these are the most important ones that you should know of. How do we access the object registry elsewhere in the code? Well, if you need to have access to the object registry itself. But if you have, for example, a field, then you can ask the field for the object registry, and then you can ask the object registry for an object, and that is lookup object, for example. So there is operations that you can do on the object registry. In boundary conditions, there is also wrap-up functions that make access a bit easier. So this is only if you are within some classes or boundary conditions. Yeah? On the top level, you don't have to do that because you have access to this identifier. So as long as you are talking scalarTransportFoam, you don't need to do lookups because you have access to your variables and the classes, and you can ask the classes, for example. Okay, so now I have a question for, yeah, there is another thing here. So this one is the IO object. This is used to read the, to identify the file that we want to read from. And for the time being and for the purpose of this training, you can think of it like a file handle. And so it opens the file and reads the file and gives us access to that file. So now we have T here and T here. Okay, can anybody tell me the difference? And why do I need to repeat the T? Okay. Yeah. Yeah, that's pretty much the answer. So it says that the answer was that is given here by AG is the outside T is a variable name. That's exactly correct. And the inside name is the name stored in the object registry, or maybe it is the file name. Well, in fact, this is the file name, and that is red. But what is more important in terms of C++ language, this is a literal. Yeah, so this is a string. And this is a variable name. So when the program is compiled, this becomes a memory address. And this is still a string. Okay, so they are not the same. They're completely different. And you could argue, why is this so complicated? The IO object should know this T. Well, where in fact, because the compiler went over it, this is just a memory address. And it cannot know what it was before it was compiled. So this is duplicated. And why should you care? So for most purposes, you make them the same. If you don't make them the same, you're reading a field with a different name. Well, like if you make this S, you will read the file S into the variable T. And that will give you trouble. So for most purposes, you want to keep them the same. Okay. Any questions up to here? Okay, I got a question. Could you talk about the general structure of the solver? For example, define variables, define the equation, initial boundary conditions, output field variable. I'll try. I will try, but we'll definitely talk about the general structure when we get out of this file, and we will talk about equations. I will try and talk a bit about initial and boundary conditions. Actually, we'll hit it as we modify the code anyway. Okay, so the second statement that you see here is basically doing the same thing. How is it that you navigate to the included.h files? Oh, I opened them here on the command line with this statement. Okay, and I got this line, I got out of the dependency file that was created by wmake. Okay, and as you know the source code better, you will basically know where to look. But dependency file, it tells you exactly which file it took. So that's why I wanted to show you the dependency file. The second statement. This is a this is U. This is where the velocity is read into the code or created. And there is only a single difference here. So here you see vol scalar field, and this is vol vector field. So the first one is a scalar field, a field of scalars that live in the center of the volumes, where this one is a vector field that lives in the center of the cells. So this is the velocity, obviously, and this is the temperature. And so this is actually 3 numbers per cell if you want, and this is 1 number. Okay, I got question, what is the ln include directory and why does it show up so often in the source code? Can you tell me? Because it's not in the source code. At least it's not on my screen, and it's not in scalar transport form. I think I'll come back to the ln include directory. So it's well, I think it's somewhere else, but we haven't touched it yet. But I'll try and pop it up later. I'll come to it. Okay, so now we have a bunch of variables here. We made a variable t and a variable u. And I'll come to another piece of object here. So this is an IO dictionary of transport properties. Again, this is read via an IO object. And this references dictionaries where you can put properties in your case. For in this case, you want to put in the diffusivity in your transport equation. That is coming in a dictionary. And usually you'll find these transport properties in constant. So this is why it says runtime constant here. And once the dictionary is read, the file is read, you can pick up properties with these constructors. So here it makes a dimension scalar, dt, by looking it up from the database. So dimension scalar is just one number. So it's a scalar with dimensions. And we can use those in operations modifying the fields or in transport equations. No, with the ln, we have the ln include as well. So that is an answer to the question that I have here. Okay, let's go back here and move a bit on and look at the working part of the program. So create fields, we are done. I'll skip this one. This is the working loop. So it goes simple.loop. It basically, this one says, increase the time step until you are finished. And the controls for this you will find in system control dict. So this loop will keep running until the end time is that you specified in system control dict is reached. And inside there is another loop. This is for correcting, doing non-orthogonal corrections. Again, this one you get from system FE solution. This is where the non-orthogonal correctors are specified. And the working bit is one line. It says solve and a transport equation. So time derivative plus convection minus diffusion. The variables, most of them we have seen already. So there is t. This is our volume scalar field, our variable volume, our volume scalar field t that is defined in create fields on the very beginning. dt, we have also seen in create fields. If I can remind you that that was the one that we read down here. And there is this phi. This is called, this is what we call the fluxes. And these are velocities, but they live on the faces. And there are reasons why we can't use the velocities straight away here. So we need to create another object. And this is done in down here in create phi. So I don't want to hide it away and from you, but there isn't much room, not enough room in this training to explain this exactly for you. Aha, this is a good one. And the question is, what is the difference between FVM and FVC? We haven't touched FVC here. So there's only FVM here. FVM and FVC, so if you talk C++, they are namespaces. But the real difference in terms of OpenFOAM are that FVC methods, they return fields. So they are doing an operation and return a field, like taking the gradient. FVC : grad of t will return the gradient, and it is a volume vector field, for example. Or if you go the curl, yeah, of u, so FVC : curl u, you will return the curl, and that is a vector. Okay, and FVM, in contrast, it will create matrices. It will return matrices. So I think a better way would be to say that it returns linear equation systems, because it's the matrix, like the rectangular matrix, plus the source term. And it comes from the discretization of the operators. The question is, where is FVM, FVC, DDT specified? That is, if you go into the finite volume library, then the namespaces are defined there, and the methods are defined in there. So this is all the job of the finite volume library. Okay, so what happens here is that these three statements, they return bits of the linear equation system that arises from the scalar transport equation. So we get a piece for the time derivative, we get a piece for the divergence, the convective term, and a piece for the diffusion. They are all added together. Then they are given to the solve statement, and that one returns the solution. So it spins up the linear equation solver. And at this point, you also get this output solving for t, and it gets returned. So I have a question for you. So how does solve know where to put the solution? I mean, why doesn't it put it into some other variable? I mean, okay, we don't have another scalar field defined in this application, but how does it know? Okay, so all of these methods, yeah, like FVM DDT, FVM diff, yeah, yeah, exactly. It's an argument here to these methods, and all of these methods, they return a matrix, the FV matrix. And the FV matrix, they all keep references to the field that were used to create them. So T, T, T. And all the operators here, they will make sure that it's always the same field that we are working on. And the solve therefore knows what is the argument that has been used in the creation of the matrices. And it has also been ensured that they are the same. Sorry. So that's basically what is happening here. And there is quite a lot that is happening in this simple line of code, yeah, and that is the beauty of OpenFOAM, because you can experiment with sets of lines of transport equations. Yeah, and it's very simple to code in new transport equations. And this was the original idea of OpenFOAM, to make implementation of transport equations very easy. And this training is just there to demonstrate this. So with the knowledge that you have now, well, you have enough knowledge now to actually do this job, like adding another transport equation. Well, you don't have quite enough, but at least on the source code level, you have enough knowledge to add new transport equations by copying and pasting. Yeah, okay. So the question was here, does this solve take the control specified in the FE solution files? Yes, exactly. And we will hit problems that will explain or demonstrate that this is the case. Okay, so now what I will do now is we'll take a case, run scalarTransportFoam on it, and start modifying our application. Okay, so I'll close this and I will go back to my training. Training. Okay, so the first thing is we need a case, and I will make this quick. There's another variable, so you can call it tutorial. They are organized in the same physics segments. So when you're looking for a tutorial for a code, or somebody told you use icofoam for this or that, then you can find the tutorials by finding the icofoam tutorial. And they are sorted in the very same way as the solvers. So we find our tutorials for scalarTransportFoam in Foam tutorials as a variable, basic scalarTransportFoam, and I'll pick the PITS daily case. Here it is. So as in the cavity, we have to run block mesh. That gives us the block mesh. I'm not going through this. So this creates the mesh. And we can run scalarTransportFoam on it. And this creates the solution. And each of these lines here is emitted from this solve statement that we just watched in our executable. I'll have a look at the code, at the output, and I will do this quickly because parafoam and block mesh is not the purpose of this training. So I'll read the temperature, and this has been the result, and it starts from 0. This is the 0 directory, and I go slowly. So T is injected here, and it is at the inlet. The outlet is on the right-hand side, and it starts going through the domain and starts filling the domain. So this has a recirculation zone around here. Okay, you can also visualize some. No, this is not what I wanted. I wanted this guy. Okay, so you start seeing the recirculation zone. Okay. So note this flow field is fixed. So we are not solving for the velocity. We are just solving for the scalar t with a frozen flow field. That's why we only have one transport equation in the top level code. Okay. So any questions about the case? Happy with this? Okay. So everybody on board. That's very nice. So if we look at this, there's a bunch of time directories. We looked at them, system, constant. You should be pretty familiar with that. And we'll take this case and modify it and add the transport equation to the code. But we will have to do changes to the case and run it as well. So what I will do, I will put this one to the side. Okay, so this is where I can run my case, and I will open another terminal. And here I will copy the source code. And solvers, basic, scalarTransportFoam. So I'm copying the directory that we have been inspecting. Why do I do that? Well, because I would like to modify scalarTransportFoam. And if I do that in scalarTransportFoam and I'm in a multi-user environment, I will change it potentially for everybody else. It's also not a good idea to change it for myself because I will probably forget about those changes. So it's good practice to change the application that you are about to change and change the name of it. So I will change the directory name. I will go in here. I will also change the C file. And obviously, this will break the make system. Because if I type wmake, it will say that it still looks for scalarTransportFoam. But I just renamed it, and therefore it cannot find it anymore. So we'll need to find out where to change the name of the C file and also the target, where the name of the executable that is generated from the source. And this is in make files. So if I open this one up, very simple. So what you see in make files is a list of files to be compiled. Okay, there is only one. We will change that from scalarTransportFoam to my scalarTransportFoam. And in this line is the target or executable that is generated. And we will call that my scalarTransportFoam. And that will make sure that when I compile it again, first, the compilation seems to work because now what is in make files matches the file system. And if you look at this line, my scalarTransportFoam is being generated. And I can take this and run it on my case. Oops. Oops, Ah, okay. I shot myself in the foot. Big time. So this one we need to throw away. Sorry about that. I picked up scalarTransportFoam from the wrong distribution. This is okay. So why are you not, why don't you like me? So okay, I seem to pick up the wrong executable. Still, okay. Okay, something is wrong with my path, but okay. So this is the executable. that has been generated. Yes, so WMake compilation is okay, and but I don't seem to pick up this my scalar form. Anyway, this works, and I should have the info statement up here. Here we go. Calculating scalar transport. So this is what I wanted to discuss with you anyway. So when you copy the code, usually what the first thing I do is compile it, see if it is running, and then put in an info statement like here to make sure that I'm actually picking up the correct executable. And we seem to have I seem to have a problem here. And yeah, it's quite possible that I pick up an old one. And obviously I pick up an old executable, and it's not, the path is not correct, is not set correct. So I'm picking up the wrong executable, and that one failed. But if I take this one, it works. Shouldn't be like this. But what you do is just put in an arbitrary info statement, make sure that you actually run the code that you changed. So that is good practice. And this could have happened just silently. And maybe the code would have worked, and I would have picked up an old executable. And yeah, you see that these things happen. And just put it in and make sure that you're actually running the correct code. So we'll leave it in. And give it some meaningful, some running at VT training. Okay. So if we want to see that, we need to compile it again. So running at VT training. So everybody happy for the moment? Can we continue like that? We should be able to put my scalarTransportFoam, but I don't really want to try, because the point is to move on and modify my scalarTransportFoam. And as long we know that we are picking up the right executable, so we should be fine. Okay, so the first thing that I would like to do with you is adding a source term, because that gets us a bit further towards playing with OpenFOAM. And I would like to add a constant source term. So something like 1 Kelvin per second. Well, I think that's not enough. I think we need something like, we'll increase. So how would I do that? Any suggestions? So it needs to go here into our transport equation. Okay, and the way that we add the source is we equal source. So there are more elegant ways these days, like these FV options in the vanilla version. But I would like to do it in the traditional way, just because it's demonstration of the basic capabilities of OpenFOAM. So source will be a variable, and that one we need to define and read in create fields as well. So what type of variable do we need to make a constant source? Yes, so dimension scalar maybe. Yeah, dimension scalar is good. We have one here. Exactly. It's just a single number and it is not spatially varying. Correct. So we'll make it here, copy pasting the dimension scalar dt. We rename it source and call it source. Then we compile our code. And I will run it on our case and it will fail. But I also want to show you error messages so that you can deal with the error messages on your own in future. So what it says is, it says keyword source is not defined in this dictionary. And this tells you, this error tells you a lot how OpenFOAM is working. And because we just added, well, we added 2 lines, yeah, but obviously we are not getting past this line here. Because this is what happens here is read, create the variable source by reading it from the transport dictionary with the name source. And what happens is it cannot find it. Well, that's not surprising because we haven't added it yet. Okay, so but this is how, in principle, how OpenFOAM works in general. Yeah, there is a lot of lookups that are scattered in the code in different classes, and they're picking up values from dictionaries. And this is how the error messages are generated in OpenFOAM, and that is why they are sometimes not so easy to understand. So if we want to make this code work, we need to go into transport properties. This is exactly the file that it's complaining about here, and add our source term. So again, easy to do. We copy that line. Yeah, we call it, we make a new entry. And add a source. Let's make it 10. Okay, and we will run it. We don't have to recompile because we haven't changed the source code. We have changed now the input deck for our case. Okay, so again, still not happy. We have an error. And it says incompatible dimensions. Yeah, I know. But again, this is I want to change the, I want to show you the error message. We have incompatible dimensions for an operation, and the operation is right here. So we are adding the variable to our FE matrices here, and it figures out that the source term has the wrong dimensions. So basically, this tells you another thing about these equations. They are dimension checked at every point. Yeah, exactly. So the question, my next question would be, what would be the dimensions of source? Kelvin by temperature, Kelvin by T, so kelvins per second, and Y I can read from the equation. So T is Kelvin, and ddt is 1/second, gives us a source term of 1/seconds. So if we do that, and at the moment we have meters squared per second, and yeah, it's not the same. So kilograms, meters per second, and we need a 0 here. So now we have Kelvin over seconds. Yeah, it's also in the error message. Exactly. The source is 2 and it's wrong. Yeah. Okay, it runs. This is very nice. We run ParaView, we go to the last time step, we look at the temperature, we scale it. Okay, and it looks different. Yeah, it used to be red here, going around here, and now it's red on the bottom. And if you look at the scale, it goes up beyond 1, and it used to be between 0 and 1. So this source is doing something. That's a good thing. So, any questions up to here? You happy with what we're doing? Yeah, goody good. Okay, so now we want to add a transport equation. So we go into my scalarTransportFoam, and what I would like to do, I will add a transport equation for a variable. Let's call it S2. So so I'm solving the same scalar transport equation. Now let's make it without the source. And now we need to define this variable or read it in. So for this, we copy the constructor, the T constructor, and rename it S2. Okay. Now we can compile this. Okay, and now if we run it, it complains that it cannot find a file 0s2, which is happening exactly here, where we're trying to read S2. So S2, and that's not surprising because we haven't defined that field. We have T and U in the 0 folder, but we need an S2. So we'll make ourselves one. We open it. Okay. And we will give it some other dimensions just for the fun of it. And we'll leave the rest. You can change this one. Okay, look. Go back and run it. Okay. Now, obviously that S2 has been accepted, read in, but there is a bunch of settings that are now missing. And these settings are in FE schemes and FE solution. And they have to do with how the equation is discretized and how the linear equation system are solved. And this goes back to an earlier question that we had here in the chat. So what is used in the discretization, and how does OpenFOAM know what is what should be used? And that basically it goes back into lookups. So for the convection scheme, this guy here is used, phi t, but needs to be S2, and we use the same settings, but we can make it upwind, but this is not important. And we will also have an issue with the Laplacian because it wouldn't know how to discretize that. So we add that one, that guy. And the DDT term will work because it uses the default value. Now, in the solution, we specify the solver for T, but we need one for S2 as well. So now we got it to work. We now have, you notice that the output has changed. There used to be one line per time step, and now we have two. Also, if you look at the output directory, there's output for S2. So the file, the file, the S2 has been read, and we can also look at it in ParaView. So not only adding that transport equation is easy, you can also get the fields, and all of the rest works seemingly seamlessly with that. Okay. Well, not surprisingly, this looks the same. S2 looks like our T before, apart from having different dimensions. It is the same. It has the same solution as T in the original case. Okay, so basically we succeeded. The job is done in OpenFOAM, but we can do a lot more playing with this. So do you have questions up to here? Because otherwise I will start playing around with the equations. Yeah, exactly. Okay, so if I want to couple two equations or any equations, I can just reuse the variables. So I can use S2 right here. So what will happen now is that the solution of S2 is used as a source for T. And that will couple these equations. So S2 is reused in that equation. Okay. So now I have to recompile my code because I've changed the source. Okay, we can run it. And we can look at, for example, T. S2 is going to be the same, but T, if you remember, we had a maximum of 1.4 with the source of 10, and now it's well, first of all, it has changed back. It's a lot smaller now, the maximum, and there is coupling between the field S2, which is this. So basically, this S2 is the source for T. And that's why T is going beyond 1 slightly. Okay. So, okay, now we coupled them. Is this a good coupling? Well, probably not, yeah, because we are using S2 and it is changing. And so one logical thing would be, and this is the time loop, yeah? So we are using an S2 that is calculated after we are using it in T. So one algorithmic change, good change, logical change would be to solve S2 before T. And then use the new value in this equation. Because it just, OpenFOAM does it in this order. Okay, will it make a big difference? I don't know, but you can try. And that's what OpenFOAM is about. You can change the order, you can put a loop around it, you can solve it multiple times, you can see whether it converges. You can also make them coupled in two ways, like using T inside of S2, like K and epsilon, they are coupled equations. And this is exactly what OpenFOAM is about. Playing around with numerical equations in an easy manner. Okay, I'll take more questions because I think we have 5 minutes left. Okay, non-orthogonal corrector. Well, if some of the, let's say the equation is nonlinear. ln include. Okay, I'll take those two. Let me start with the non-orthogonal correctors. So what we're solving in solve is a linear equation system. Okay, if your equation is nonlinear, yeah, and I can do that very, very easily here. Yeah? Okay, so I get say, we'll use some power and we will need some constant here to make that dimensionally. Now it's, or we make it, I don't know, depend on, make the equation nonlinear. Then whatever we solve here is a linear equation system. And so some updates will be lagged. And this means that we have to solve multiple times. The same thing happens with the mesh. So if you have a distorted mesh, and the more badly it gets, there is, from the discretization, there will be things placed in the source term, and they depend on the state variable. So you have to solve it multiple times on the bad mesh to make it converge. And this is exactly what this loop is about. So on a bad mesh with certain discretization schemes, you need to solve it multiple times. And this is what the loop is doing. But it can also, the way that you would solve nonlinear equations is just the same way. Okay, I hope this answers the non-orthogonal. The ln include. Okay, let me do the ln include first because that one was asked before. So ln include, the way the make system deals with the locations in OpenFOAM is through a file called make options. And in here, ln include appears. Okay, so the only library that we need, well, actually there's two libraries that we need to make this example run, the scalarTransportFoam, and that one is finite volume and one is OpenFOAM. OpenFoam is included automatically. So the only one that's left is here. And this ln include directory, because the source code is built with a directory structure. So every class has its own directory. You would have to include for the compiler all of these directories. And this is not feasible. So the way that the make system in OpenFoam works is per library, it links all the files that belong to the library into ln include. And then we only have to include the ln include directory for the respective library. There are downsides of it. But anyway, that's why we have ln include. Does that answer the question about ln include and where it pops up? SM is ready, and SM is happy.
All right, so I think that we are going to have to wrap up because we've reached time.
Yeah.
But this is a really, really awesome conversation, and I'm so glad that we've got so much participation and questions from the audience here. So for everyone, if you have more questions or if you want to continue the conversation, you should be able to do so via the Whova app, or otherwise, you know, if you want to reach out to Henrik, you know, he can provide any information about that. Thank you so much for this fantastic training. This has been recorded, and so we will be keeping everybody posted about where they can view this training for future reference. And once again, thank you to everyone, and especially for thank you to today's speaker.
Can we take out the glitch? Anyway, thank you very much. Bye-bye.